In this lecture we are going to start the concept of canonical correlation analysis. Now, in canonical correlation analysis what we try to do is the following thing. We try to explain the covariance structure, or rather the correlation structure between two sets of random vectors in terms of fewer linear combinations. What I try to convey is the following. Let us look at this concept, canonical correlation analysis. Now, the setup for the canonical correlation analysis is the following. We have a random vector p x p dimensional, and we have another random vector y q dimensional. Without loss of generality, we assume that p is less than or equal to q. If not, then we can rearrange and make the first set of random vectors to be having components p, which is less than or equal to the number of components of the second random vector y. Now, these random variables are such that expectation of x vector, that is equal to mu x vector, and expectation of y vector is equal to a vector which is mu y. Now, the covariance matrix, variance covariance matrix of x is denoted by sigma 1 1. The covariance matrix of y is denoted by sigma 2 2, and the covariance matrix between x vector and the y vector is given by sigma 1 2, say, is equal to sigma 2 1 transpose. That is, the covariance between y and x would be sigma 2 1. So, the transpose of that will be equal to sigma 1 2. That is, if we look at this augmented random vector x augmented with y, this is a pq dimensional random vector. This is such that the covariance matrix between x and y is going to be given by the matrix which has sigma 1 1 in the first block, which is of the order of p by p. So, this of course is p by p matrix, this is a q by q matrix, and this sigma 1 2 is going to be a p by q matrix because it is a covariance between x and y. So, this sigma 1 1 here, sigma 2 2 here, sigma 1 2 and sigma 2 1. Now, we assume that this sigma 1 1 is greater than 0, and so is sigma 2 2. So, we will have the two variance covariance matrices of the respective random variables x, random vectors x and y, to be having the variance covariance matrix which is positive definite. Now, as I said that the basic concept in canonical correlation analysis is we look at such random vectors p dimensional x and a q dimensional y, and then try to explain the correlation structure of these two random vectors. Now, what will be the correlation from here? When we have this as a covariance between x and y given by this, pre and post multiplying this matrix by the square root of the variances, we can get to, from here we can easily get to the correlation matrix between x and y. Now, canonical correlation purpose is to express, or rather explain, the correlation structure between this x and y in terms of a fewer linear combinations. Now, when we talk about linear combinations, we look at the following. Consider linear combinations. Say a prime, or rather a I prime x and b I prime y for a fixed number of I equal to 1 to up to, say, any order m. Right. So, these are linear combinations of possible linear combination of x's, these are linear combinations of y. Now, if we look at the covariance between any a prime x and b prime y, then that is going to be given by the covariance between a I prime x and b prime y, that is going to be a prime, the covariance between x and y. Now, what is the covariance between x and y? In the formulation that we had here, covariance between x and y is sigma 1 2. So, this is going to be equal to sigma 1 2 times B primes transpose, which is B. So, this would imply that the correlation between A prime x linear combination and B prime y, this linear combination, is going to be given by the covariance between the two linear combinations. These are scalar random variables now, after we are taking linear combinations. This divided by the standard deviation or the square root of the variances of the respective terms. So, the variance of A prime x will be equal to A prime sigma 1 1 times A, this into the variance of B prime y, which is B prime sigma 2 2 times B in our defined notations. So, this is the correlation coefficient between A prime x and B prime y. So, the purpose of canonical correlation analysis is to explain the correlation structure between this x vector and y vector in terms of a few linear combinations. Linear combinations of the form that it is A I prime x and B I prime y, right. Now, how are we going to have such linear combinations, and what sort of linear combinations should we consider when we are looking at expressing or trying to explain this correlation structure between the two sets of random vectors x and y? Let us look at that particular formulation, how we are going to actually define the pairs of canonical variables. So, let me first give the definition of first canonical variable pair. First canonical variables, first pair of canonical variables actually. So, let me give the definition of this. Consider u1 equal to a1 prime x and v1 equal to b1 prime y, such that number 1, variance of u1 is equal to variance of this variance of u1 equal to variance of v1 is equal to 1. So, we will have the linear combinations thus formed. Number 2 is that the correlation between this u1 linear combination and v1 linear combination is the maximum correlation between A prime x and B prime y, such that this maximization is over A and B. So, we are looking at u1 and v1 to be linear combinations such that u1 and v1 has got variance unity, and the correlation between the two linear combinations u1 and v1 is the maximum correlation that one can find if one looks at all possible linear combinations A prime x's and B prime y. So, this maximization is over A and B. So, if we have u1 and v1 such that these two conditions are satisfied, then u1 v1 is called the first pair of canonical variables. Right, and this rho 1 star, which suppose denotes this maximum over A and B of these linear combinations A I prime x's and B prime y's, this is what is called is the first canonical correlation coefficient. Right. So, this is how the first canonical first pair of canonical variables are formed with the corresponding first canonical correlation coefficient, which looks at all possible linear combinations and between x and y, and then tries to look at one that maximizes that particular linear combination. The maximizes the correlation coefficient between all possible linear combinations. Now, given this as the definition of the first canonical correlation pair variables, second pair of canonical variables are going to be defined. Canonical variables. Let me first give the definition of the second pair of canonical variables. Consider linear combinations A prime x and B prime y such that, number 1, A prime x is uncorrelated with the first canonical variable, that is covariance between A prime x and u1, where u1 is the first canonical variable which we have defined in here. So, this is the u1. So, u1 is the first canonical variable. So, the correlation between A prime x and u1 is equal to 0 is equal to the correlation. I am just writing covariance, because if covariance is equal to 0, then correlation also is equal to 0, which is equal to the covariance between B prime y and V1. So, we will have these linear combinations A prime x uncorrelated with u1, B prime y uncorrelated with V1. Then under this condition, additionally we will have this A prime x is equal to variance of B prime y is equal to 1. So, we are considering all such linear combinations such that these two conditions are satisfied, and under such conditions, let me put a number star here, then maximize the correlation between A prime x and B prime y such that this star is satisfied. Right. The maximizing A2 prime x and B2 prime y, say, let me have this notation, are called the second pair of canonical variables. And the maximizing correlation coefficient is called the second canonical correlation coefficient. Canonical correlation coefficient. So, what is the second pair of canonical variables? We look at all such linear combinations now restricted to the situation that these linear combinations will be uncorrelated with the first canonical variable. The respective components B prime y will be uncorrelated with the first canonical variable pair component, which is associated with y with unit variances, and then we will try to maximize the correlation between A prime x, all possible A prime x and B prime y's, such that the condition star is satisfied, and the solution, the maximizing, this is the maximizing A prime x and B2 prime y are called the second pair of canonical variables, and the coefficient that we are going to obtain by maximizing that expression, the correlation between all such linear combinations such that this star is satisfied, is going to be called the second canonical correlation coefficient. Now, we can write thus the kth canonical variables definition. It is going to be that pair which is going to be uncorrelated with all the previous k minus 1 pairs of canonical variables, and subject to the condition that we are looking now at linear combinations a k prime x's and b k prime x's, such that we will have all those previously obtained canonical variables uncorrelated with this particular set, and with respect to that particular restriction we try to maximize the correlation once again in order to get the kth pair of canonical variables. Let me write the definition here. So, the kth pair of canonical variables are the linear combinations say u k v k having maximum correlation unit variance property, having unit variance which maximize the correlation among all possible linear combinations, uncorrelated with the previous k minus 1, uncorrelated with the previous k minus 1 canonical variable pairs. So, this is how the pairs of canonical variables are actually obtained. Now, we will have to look at what finally turns out to be the canonical variable pairs, and how we can actually get to the canonical variable pairs sequentially, starting from the first pair of canonical variable pair and then maximizing the correlation, and then moving forward to second, third, fourth and kth pair of canonical variables. Right. Now, in order to actually derive, we will derive the canonical variables. In order to derive, we will look at this structure as before, that this has got the covariance structure as equal to sigma 1 1, y, this is p by 1, this is q by 1, such that the covariance matrix of y is given by sigma 2 2, wherein as before we will assume that sigma 1 1 is greater than 0, sigma 2 2 is greater than 0, and thus we will have the covariance structure between x y, this vector, to be given by sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. Now, this matrix also is positive definite. Now, consider a matrix A to be equal to sigma 1 1 to the power minus half. Sigma 1 1, remember, is positive definite. So, sigma 1 1 to the power minus half can be defined, multiplied by sigma 1 2 times sigma 2 2 to the power minus half. Now, such a matrix plays a major role in canonical correlation analysis. Now, from this matrix A, if we look at the matrix which is A prime, now A prime matrix would be given by this sigma 1 2, then A transpose of this particular matrix. So, we will have this as sigma 2 2 to the power minus 1, transpose of this would be sigma 1 2 1, and then the transpose of sigma 1 1 to the power minus half is the same matrix itself, and A prime A is going to be sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus 1, sigma 1 2 times sigma 2 2 to the power minus half. So, these are two matrices A prime, where A is defined by this matrix. Now, A prime, what is the order of this matrix A? this is P by P, this is P by Q, and this is Q by Q. So, this has an order which is P by Q. So, this A prime matrix is of the order P by P, and A prime A matrix is of the order Q by Q. Now, we note the two following important observations, that this A prime A, let me define these eigenvalue eigenvector pairs. Let lambda 1 greater than or equal to lambda 2 is greater than or equal to lambda 3 greater than or equal to lambda p, eigenvalues of A prime matrix, say, and mu 1 greater than or equal to mu 2 is greater than or equal to mu q, which are eigenvalues of A prime A, right. The two things are quite obvious from the formulation, which I put it as two separate notes, that A prime A and A prime are positive semi-definite. So, I write it as greater than or equal to 0. This will imply that this lambda i's are greater than or equal to 0, and mu I are greater than or equal to 0 for every I. Let me just write it as j, not to mix up with the two. So, lambda I is greater than or equal to 0 and mu j is greater than or equal to 0 for every I j. What more is that the non-zero eigenvalues of A prime A and the non-zero eigenvalues of A prime are identical, only the eigenvalue 0 will have different multiplicities in A prime A and A prime. So, non-zero eigenvalues of A prime are same as the non-zero eigenvalues of A prime A, and this eigenvalue 0 has different multiplicities in A prime and A prime A if we have Q to be strictly less than P, right. So, this is a simple observation, because we will have A prime A and A prime being defined through this particular type, and as we will see in the next derivation, and furthermore that such matrices play a major role in canonical correlation, derivation of the canonical correlation variables. So, we are moving on to derivation of first pair of canonical variables. We have the following result. Let me first state the result. Suppose we have, with the previous setup, P is less than or equal to Q, and covariance matrix of x and y, as we are denoting that by the following matrix: sigma 1 1, sigma 2 2, sigma 1 2, sigma 2 2, and consider the linear combinations rather, consider the linear combinations, say u equal to A prime x and v equal to B prime y, then maximum over A and B correlation between A prime x and B prime y, let us denote that by rho 1 star. This is a maximizing correlation between this, is attained by the linear combination linear combination U. This is the linear combination that we are going to obtain, which is going to be given by E1 prime sigma 1 1 to the power minus half times x and V equal to F1 prime sigma 2 2 to the power minus half times y. We are going to define what this EI primes and F1 prime are. So, this U and this V will constitute the first pair of canonical variables. So, this is the first pair of canonical variables, where we have rho 1 star square greater than or equal to rho 2 star square is greater than or equal to rho p star square are the eigenvalues of that A prime matrix, which is sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus half. So, this maximum linear combination, that the correlation coefficient between the linear combinations rho A prime x and B prime y, this is going to be attained at the value rho 1 star, where rho 1 star is nothing but they are the square roots of the eigenvalues of this sigma 1 1 to the power minus half 1 2 2 1 minus 1 sigma 2 1 sigma 1 1 to the power minus 1 matrix, and E1, E2, EP are the orthonormalized eigenvectors corresponding to our rho 1 star square, rho 2 star square, rho p star square. So, these are the eigenvalues of that A prime matrix, and these are the corresponding orthonormalized eigenvectors corresponding to that. And furthermore, rho 1 star square, rho 2 star square, rho p star square are the p largest eigenvalues, of the matrix which is A prime A. So, that matrix would be given by sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus 1, sigma 1 2, sigma 2 2 to the power minus half, right. So, these are also means what we had seen earlier by defining that A prime, the two A and corresponding A prime A are these two matrices, and we had noted that if we are going to play around with A prime and A prime A, the non-zero eigenvalues of the two matrices will be exactly the same, only the eigenvalue 0 will have different multiplicities in the two matrices, which are these two matrices, and we are basically writing that here, that rho 1 star, rho 2 star, rho p star are the p largest eigenvalues of this particular matrix, and with eigenvectors as f1, f2 and fp, these are also orthonormalized eigenvectors corresponding to rho 1 star square, rho 2 star square, rho p star square, which are there corresponding to now this A prime A matrix, which is given by this. And we will also have the following, where each fi is proportional to the following, which is sigma 2 2 to the power minus half, sigma 21 sigma 11 to the power minus half times E1. So, this is the relationship between the eigenvectors of that A prime matrix, which were E1, E2, EP, and F1, F2, Fp are the orthonormalized eigenvectors corresponding to the P largest eigenvalues which match the eigenvalues match for the two matrices, and the eigenvectors, the orthonormalized eigenvectors, basically satisfies the relationship that each of these Fi primes are going to be proportional to this sigma 2 to the power minus half 2 1 sigma 1 1 to the power minus half E1. Now, this is proportionality constant can be easily computed by noting that the norm of Fi's should be equal to 1, right. So, this is the entire result which is going to help us or rather this is the result which tells us what is actually the first pair of canonical variables, right. We will look at proving this particular result because it is a fundamental result in canonical correlation analysis. So, we will actually prove this result, and let us, in order to do that, look at this correlation between linear combinations A prime x and B prime y. So, as we have seen, this is equal to our A prime sigma 1 2 times B, this divided by A prime sigma 1 1 times A, that multiplied by B prime sigma 2 2 times B, this raised to the power half, right. Now, in this particular expression, let us define this sigma 1 1 to the power half A, that is equal to a vector C, and sigma 2 2 to the power half times B vector to be equal to a vector which is equal to D. That is, our A vector is equal to sigma 1 1 to the power minus half, sigma 1 1 and sigma 2 2 are positive definite. So, this is defined, and this B is equal to sigma 2 2 to the power minus half times D. Now, with this notation here, what we will be having, the correlation between A prime x and B prime y, these A's and B's are now going to be replaced by C's and C and D rather. So, what we will be having in the denominator is the following. Now, A is equal to this particular term, sigma 1 1 half A is equal to C. So, what we will be having as C prime is A prime sigma 1 1 to the power half. So, this just is equal to C prime C. This is what this boils down to, and the second term is nothing but D prime D whole raised to the power half, and what we have in the numerator of this particular expression is that A prime is going to be given by C prime sigma 1 1 to the power minus half, and then this is sigma 1 2 which remains as it is, and B is going to be given by this sigma 2 2 to the power minus half times D. So, this is what is the correlation coefficient between the two linear combinations in terms of the redefined vectors C and D. Now, note that if we consider the numerator, which is C prime sigma 1 1 to the power minus half sigma 1 2 times sigma 2 2 to the power minus half times D, by using Cauchy-Schwarz inequality, by considering this as one vector and this as the second part, this will be less than or equal to C prime sigma 1 1 to the power minus half sigma 1 2 sigma 2 2 to the power minus half times the transpose of that. So, that is equal to sigma 2 2 to the power minus half once again multiplied by sigma 2 1 sigma 1 1 to the power minus half, this raised to the power half, that multiplied by this term d prime d whole raised to the power half. So, this quantity which is in the numerator is less than or equal to this term when we are applying the Cauchy-Schwarz inequality. Let me give an equation number to this, because later on we will be using these equations in the derivation. So, let us now look at this particular term. Well, a term C is missed out here. This is C. So, this is C prime sigma 1 1 to the power minus half sigma 1 2 sigma 2 2 to the power minus half by combining these two matrices, that multiplied by sigma 2 1 sigma 1 1 to the power minus half times this vector C. Now, we will look at this term here and see if we can provide an upper bound to this particular term here, which of course is very simple. We recall this particular result. So, if we look at the right hand side here and the first expression, if you are trying to get an upper bound of this expression, we make use of the following result, that I will say as a recall of matrix theory result. Recall that if this B is real symmetric matrix with eigenvalues and eigenvectors, let this B be P by P, eigenvalues lambda 1, lambda 2, lambda P in this order, and eigenvectors orthonormalized, as E1, E2, EP, then we have this following result, that if we are trying to maximize the quantity which is x prime b x, that divided by x prime x, this is maximization over all possible x's. This maximum value is nothing but equal to lambda 1, the largest eigenvalue of this real symmetric matrix, and this maximum is attained at x equal to E1 vector, right, where E1 is the orthonormalized eigenvector corresponding to the largest eigenvalue lambda 1. So, this actually will tell us that we can say that x prime b x, if we look at this expression, is going to be less than or equal to lambda 1 times x prime x, where the equality once again is attained if we choose x to be equal to E1. In that case, this will be equal to 1 and this side will just be equal to lambda 1. So, this is what is the result which we will make use of in order to provide an upper bound of this particular quantity. Why do we look at that? We will consider this entire matrix here, which in our earlier notation is equal to A prime matrix, and then look at its eigenvalues and eigenvectors, and using this particular result we will be able to say that this C prime, where is that? This is C prime sigma 1 1 to the power minus half sigma 1 2 sigma 2 2 to the power minus 1 sigma 2 1 sigma 1 1 to the power minus half times this C vector. This, using this expression, would be less than or equal to the corresponding eigen vector of this matrix, which we have earlier denoted by rho 1 star square times this C prime C, with equality attained at, I will give this as equation number double star. Equation number star is defined earlier for this expression. So, we will have this less than or equal to this term. In the above, in the equation number double star, equality is attained at, now where will the equality be attained? We are looking at rho 1 star square as the eigenvalue, the largest eigenvalue of this particular matrix. We are going to say that this is less than or equal to rho 1 star square times C prime C, and equality of course will be attained as in the previous general result at the eigenvector, orthonormalized eigenvector corresponding to rho 1 star square. So, this equality will be attained at C equal to E1. Now, if we have equality attained here, we will also look back at the equation number star as to when the equality is going to be attained in this expression star. Now, equality in expression star will be attained if we have this vector proportional to this particular vector. So, we will put in that condition also, and in single star equation equality holds if we have d to be equal to sigma 22 to the power minus half, sigma 21, sigma 11 to the power minus half times E1. Why is that so? Because if we are looking at this expression, here equality will hold if we have d equality if d is proportional to this particular vector, which is sigma 22 to the power minus half sigma 21 times sigma 11 to the power minus half, right, times this vector c. Now, in double star we require c to be equal to E1 in order to have equality, in order to attain the maximum value, and here in order to attain its maximum value we would require this, and since in double star equality holds for c equal to E1, here also c needs to be replaced by E1. So, we will have these two to hold if we want to have equality in all the previous steps. That is, we would require this c vector to be equal to A1, which is equal to c is connected with a vector because a was the original vector. So, this will imply that the maximizing a vector is going to be given by sigma 11 to the power minus half times E1, right, and the b vector which is connected with the d vector through this, that b is equal to sigma 22 to the power minus half times d, and in order to have equality we would require this condition that d is sigma 22 to the power minus half sigma 21 sigma 11 to the power minus half E1. So, that we will have b to be equal to sigma 22 to the power minus half sigma 22 to the power minus half, which multiplied by sigma 21 sigma 11 to the power minus half times this E1, right. Now, this entire vector is what we are going to call as F1. Look at the result statement here. What we had was this Fi is proportional to this particular quantity here, and hence this is what we are going to have as F1. Now, if we look back at the expression of the correlation of those linear combinations, of the two linear combinations which were of the form A prime x and B prime y, we had seen that this was less than or equal to, let me look at that expression where we had that. So, this correlation between this term was equal to this, which we had seen that the numerator is less than or equal to this, and hence we will have this correlation between A prime x and B prime y to be given by this C prime sigma 11 to the power minus half sigma 12 sigma 22 to the power minus 1 sigma 21 sigma 11 to the power minus half times C, this divided by this our C prime C, because that d prime d term cancels out. I think it would be better if I write one more step here. So, this multiplied by this d prime d, we had the entire thing here raised to the power half. What we are doing is that we are looking at this expression here, that the correlation between A prime x and B prime y is equal to this. So, if we put the upper bound of this numerator term here, we will have the correlation coefficient between A prime x and B prime y to be less than or equal to this to the power half and this to the power half divided by C prime C d prime d to the power half. So, what we have is this less than or equal to this divided by C prime C multiplied by d prime d whole raised to the power half. So, as we see that these two terms cancel out, and this is equal to C prime sigma 1 1 to the power minus half sigma 1 2 sigma 2 2 to the power minus 1 sigma 2 1 sigma 1 1 to the power minus half times C, this divided by C prime C whole raised to the power half, right. And this expression, by using this result, what we have done here, this one numerator is further less than or equal to rho 1 star square times C prime C. So, what we have finally is that this expression is less than or equal to this one is rho 1 star square, this is rho 1 star square multiplied by C prime C, this divided by a C prime C entire thing raised to the power half. So, that this term is just equal to rho 1 star. So, this correlation between A prime x and B prime y is less than or equal to rho 1 star. So, that rho 1 star is going to be attained if we choose A equal to this and B equal to this particular term, right. Let us finish that. So, this will imply that maximum correlation between A prime x and B prime y, maximum over all possible A and B vector, this is equal to rho 1 star, and the correlation coefficient between the two vectors, which is E 1 prime sigma 1 1 to the power minus half x and F 1 prime sigma 2 2 to the power minus half y. So, these are the linear combinations that we are talking about. So, by choosing B, this is just B equal to sigma 2 2 to the power minus half times F 1, where F 1 is the eigen vector orthonormalized corresponding to that A prime A matrix. So, what we are going to have is this correlation. It is elementary actually to look at what this expression is equal to. This is E 1 prime sigma 1 1 to the power minus half times covariance between x and y, that is equal to sigma 1 2, this times sigma 2 2 to the power minus half. Oh, I am writing the entire thing here, not exactly the covariance term. So, this correlation is equal to the covariance between E 1 prime sigma 1 1 to the power minus half times x, F 1 prime sigma 2 2 to the power minus half times y, that divided by the variance of the respective terms E 1 prime sigma 1 1 to the power minus half x, that into the variance of the other term, which is F 1 prime sigma 2 2 to the power minus half times y. So, this is that particular, this whole raised to the power half, of course. This is that we are looking at this rho A prime x and B prime y with our A equal to the maximizing coefficient, which is sigma 2 2 to the power minus half E 1. So, this is sigma 1 1 to the power minus half times E 1, and with the B, which is sigma 2 2 to the power minus half times F 1, and this straight away leads us to the value, which is rho 1 star. So, that is the maximum correlation coefficient attained with A equal to this and B equal to this particular term. So, this will imply that the first pair of canonical variable is given by u 1, say u 1 equal to sigma u that equal to E 1 prime sigma 1 1 to the power minus half times x, and the second component V1 is equal to our F1 prime sigma 2 to the power minus half times this y. So, this is the pair of the first canonical correlation. Now, from this expression also we had another point to prove in the result. Now, note that we have this sigma 1 to the power minus half, sigma 1 sigma 2 to the power minus 1, sigma 2 sigma 1 to the power minus half times. Now, this is the matrix which has eigenvalues as lambda i's and eigenvectors orthonormalized as ei's. So, this times E1 vector will be equal to lambda 1. I will just write lambda 1, or rather lambda 1 is nothing but this rho 1 star only, right. So, that is the eigenvalue. So, I am just writing lambda 1 that times this E1. Now, starting from this particular equation here, this will imply that if we pre-multiply the left and the right hand side with this expression, which is sigma 2 to the power minus half, sigma 2 times sigma 1 to the power minus half. So, this matrix, if we pre and post multiply on both the sides, what we are going to get is the following, that it is sigma 1 to the power minus half, sigma 1 sigma 2 to the power minus 1, sigma 2 sigma 1 to the power minus half times E1, that is equal to lambda 1 or rho 1 star times sigma 2 to the power minus half, sigma 2 sigma 1 to the power minus half times E1. Now, let us look at the left hand side here. This sigma 2 to the power minus half, sigma 2 and this expression is sigma 1 to the power minus 1. We take the next term also, sigma 1 and split this particular term in terms of sigma 2 to the power minus half and another sigma 2 to the power minus half. So, let us write this as sigma 2 to the power minus half times whatever is left. So, this has still a sigma 2 to the power minus half times sigma 2 into sigma 1 to the power minus half times this E1, that equal to lambda 1 or rho 1 star times sigma 2 to the power minus half, sigma 2 sigma 1 to the power minus half times E1. So, we are basically denoting this as F1, that is, this is F1, and if we look at this particular matrix here and go back to the result that we had stated when deriving the first pair of canonical variables, then you will find that this is the matrix that we had talked about at the end of the result, which is that furthermore these are the p largest eigenvalues of the matrix sigma 2 to the power minus half, sigma 2 1 to the power minus 1, sigma 1 sigma 2 to the power minus half, with these as the eigenvalues, where f i's are proportional to this particular quantity, and that is what precisely we have obtained, that this is the matrix, the eigenvector is F1 which is proportional to this term, that is equal to lambda 1 is rho 1 star times this F1. Thus, we conclude from the previous expression what we have got, that if we have this equation to be satisfied, say star prime equation, thus if we have lambda 1 E1 is the eigenvalue eigenvector pair, eigenvalue eigenvector pair of this sigma 1 to the power minus half, sigma 1 sigma 2 to the power minus 1, sigma 2 sigma 1 to the power minus half, then this lambda 1 F1 with F1 normalized form of the vector, which is sigma 2 2 to the power minus half sigma 2 1 sigma 1 1 to the power minus half times E1, is the eigenvalue eigenvector pair eigenvector pair of this sigma 2 2 to the power minus half sigma 2 1 sigma 1 1 to the power minus 1 sigma 1 2 sigma 2 2 to the power minus half. That concludes the proof of this particular result.